Hello, my name is Gurumurthy Ramachandran, and I'm a professor in the Department of Environmental Health and Engineering, the Bloomberg School of Public Health at Johns Hopkins University. And this is one of the modules produced by the Program on Occupational Health and Safety Education on Emerging Technologies, Mid-Atlantic Partnership, also known as Pocket Map. And this first module deals with uncertainties in physical measurements. We will start in this section with the definition of a measurement. What is a measurement? On the right-hand side of the screen, you see a variety of pictures of different types of measurements we can do. We have a weighing balance with which we can measure weights of various objects. We have a tape measure with which we can measure the length of different objects. We have a clock with which we can measure time. And we also have a thermometer with which we can measure temperature. So what is a measurement? A very simple definition is that a measurement assigns a specific numerical value to a particular characteristic of the physical world. And each one of these figures shows a particular type of measurement. For example, with a clock, we can measure the interval of time that has elapsed, or with a tape measure, we can measure the length of an object. And so a measurement system is a tool used to quantify a particular physical variable, such as length or mass or time and so on. So in this figure, we'll use this example of measuring the length of the side of a table. And so this is a process of measurement. And so there are two main measurement tasks that are involved in this. So one is to construct a suitable ruler or a reference scale. And so on the right-hand side, you see two images of a tape measure lying across the length of a table. And then the other image shows just a standard tape measure. And so this is our ruler, or the reference scale, on which there are markings that mark out inches. And the unknown that we want to measure is the length of the side of this table. And actually what we really want to do is measure the area of this table. So we need to measure the length and width of this table. And so we describe this as a rectangular table, and we measure its length and width using a tape measure. And we can end up with a statement such as the table is 2 meters wide and 4 meters long, and therefore has an area of 8 square meters. There are a number of issues with this definition of measurement. The first one is that the table is not necessarily rectangular. It sort of looks rectangular, but the edges are rounded. And so it's an imperfect rectangle at best. The second thing is, unlike a rectangle, this surface is not flat. And you can see in this right-hand side image of the corner of a table, both the rounded edge and also the different parts of the table coming together. There are imperfections on the surface. And so it's not a perfectly flat surface. It's sort of rough, and there are indentations in the wood. And the third part, which I've not shown in this diagram, is that the ruler may not be exact. For instance, the tape measure may be made out of some material that has expanded over time. So if it's a metal ruler, the metal has expanded because we are in a hot room. Or maybe it has shrunk because we are in a cold room. So the ruler may not be exact. So there is more to a measurement than this. And so here the title of this slide is Measurement as a Parameter Estimation in a Model. So in this case, we are not just looking at the measurement as I described previously, but a more appropriate statement might be that we are going to ignore all the limitations that I mentioned earlier, that the table has rounded edges, there are imperfections on the surface, and so on. And instead we say that the table is now modeled as a rectangle, having two parameters, width and length. And the best parameter estimates are 2 meters for the width and 4 meters for the length. And so what this does is this description separates the physical object, which is the table, from the parameters of our mathematical model of the table. And so our plain rectangular model is this idealized object, and which is described by two parameters, length and width. And now we are estimating the parameters of this idealized object. And so our plain rectangular model is a useful approximation of the actual physical object. We have no way of knowing the true value of these parameters. we therefore make repeated measurements of width and length parameters and then estimate the most likely value of these parameters, perhaps by averaging them. And so we come to a more sophisticated definition of a measurement, that a measurement is an estimate of a parameter in a quantitative model that represents some aspect of reality. So let me repeat that again. It's an estimate of a parameter in a model that represents some aspect of reality. And so it's important to distinguish between the actual or quote unquote true value of a physical quantity at some point in time that we think should exist, that we intuitively feel must exist, and our best estimate or measurement of it based on repeated trials using a quantitative model. Thus, a measurement is a random variable with a mean value, a variance, and confidence intervals. In this slide, I'm showing you the components of a measurement system. And so on the right-hand side, there are a series of boxes. So the measurement system consists of a sensor, a transducer, and a signal conditioning unit, and then an output. So the sensor unit uses some natural phenomenon to sense this thing that we want to measure or the parameter that we want to estimate. And I'll get into an actual example in the next slide. So following the sensor, the transducer converts the sensed information into another form that is more amenable to measuring, such as a voltage or a displacement. This signal is then conditioned by the signal conditioning unit, which modifies the transducer signal to a magnitude that is easily measurable, and it also removes extraneous noise. And then the output stage provides a numerical value of the measurement. A concrete example of a measurement system is shown in this slide, and we're going to use the example of an instrument that is used to measure airflow, and it's called a rotometer. A rotometer is essentially a tapered tube as shown on the right-hand side of this slide. There is a ball inside this tapered tube, and air enters from the narrow end of the tapered cylinder and exits from the top, which is the wider end. And the force of air pushes the sensor, the ball, upward until it comes to a place where the downward weight of the sensor ball is matched by the upward force acted on it by the air. And we measure the distance that this sensor ball has traveled along the tapered tube. So in this example, the float is the sensor, so it moves up the vertical tube, and the flow rate information in liters per minute is converted into the displacement of the floating ball. You can see the markings in inches or centimeters on the side of this tapered cylinder. And so the tapered column acts as the transducer. So it has converted this physical thing that we are interested in, namely the airflow rate in liters per minute or cubic meters per minute, into an actual distance that we can measure along the side of this tapered column. The changing diameter of the column determines the linear extent or the distance to which the float travels, and therefore it is conditioning the signal. So by adjusting how tapered the column is or how straight the column is, the sensor will travel at a certain amount of distance. So you can imagine a column that is sort of very narrow at the bottom and very broad at the top. The sensor may not travel that much distance. Whereas a more narrow column, the sensor will travel a lot more. So you can sort of figure out how much precision do we need in our measurement and design our tapered tube accordingly. And the output of this is the marked scale, which reads out the distance moved by the float in inches or centimeters or millimeters. But of course, all we have got out of this is an output in units of distance in inches or millimeter. But what we really need is the output in terms of cubic meters per minute or liters per minute. So how do we do that? How do we convert inches into cubic meters per minute? We do that using a process called calibration. And so this is the relationship between the input information as acquired by the sensor and the output information. And so this is established, the relationship between the input information acquired by the sensor and the output information is established by a process called calibration. So during calibration, a known value of input is applied to a measurement system, and the output is observed. And the known value is referred to as a standard. So in our example, what we would do is we would make a known flow rate of air into the rotameter. So we would say 5 liters per minute of airflow is entering this rotameter, and we know that it's 5 liters per minute through an independent measurement. So that's not related to the rotameter, and that is called the standard. And we would then find out how much distance the sensor, the float, traveled along the tapered cylinder, and we can mark that as the output on this graph. So on the right-hand side, you see a calibration curve, what is called a calibration curve, which shows the relationship between the input value and the output value. The input value being the known airflow rate, and the output value being the inches or centimeters that the float traveled. And so for 5 liters per minute input, we find out that the float traveled around 10 centimeters. And then we put in another known input of 1 liter per minute, and we see that the output value, the distance traveled, is about 0.7 centimeters. And we then construct for different values of input airflow rates, we find out the distance that the float traveled. And in this manner, we construct a calibration curve, a curve that shows the relationship between the input and output values. And once we have this curve, we can use this calibrated rotameter to measure any unknown value of flow rate. And so we would put in an unknown value of the airflow, attach it to the bottom of the rotameter, and we find out how much distance the float traveled. And then we say, oh, the float traveled 6 centimeters. Therefore, the flow rate, according to this calibration curve, is around 3.5 liters per minute. So that's the way the calibration curve is used to determine the flow rate through this rotameter. You see in this graph that the input values range between 0 to 6, whatever units, and I'm just using liters per minute as an example. And so this is the range over which the calibration is valid. So the maximum and minimum values define the input span of the measurement system. So the X max minus X min. And the output range correspondingly is the Y max minus Y min. That is the output span, meaning the range over which the output varies. And measurements outside this range are not advisable because we don't know how the rotameter will behave outside of this input and output spans.